Afterglows of several gamma ray bursts were recently detected with atmospheric imaging Cherenkov telescopes. One of the first of these was the afterglow of GRB 190114C. Its spectral energy distribution was measured up to the energy of about 1 TeV. Besides being important for the intrinsic physics of gamma ray bursts, such observations could in principle be used as a probe of the extragalactic background light and the extragalactic magnetic field. In this work, we, for the first time using actual data collected by the major telescopes, calculate the spectrum of the intergalactic cascade echo from GRB 190114C, assuming various extragalactic magnetic field strength values. This slide contains some convenient abbreviations and definitions used in our talk. Let me briefly review the state of the art of extragalactic magnetic field constraints. Upper limits come from Faraday rotation measurements. Much weaker, less than 100 femtogauss EGMF could be probed through intergalactic electromagnetic cascades. Indeed, the primary gamma rays partially absorb on extragalactic background light photons by means of the pair production process. Secondary electrons and positrons get deflected in the extragalactic magnetic field and produce cascade gamma rays by means of the inverse Compton process. Such lower limits coming from blazar observations usually give values from 0.1 to 10 attagauss. However, in 2018, a paper was published claiming the improvement of these lower limits by several orders of magnitude. However, a closer examination of this paper reveals that some rather strong assumptions were made by the authors. In particular, it was assumed that the cascade component does not change the total observable spectrum strongly. Actually, it appears that there is simply no room left for the cascade component in their fit. We conclude that the results are in a measure driven by their own assumptions. Actually, a reasonable fit of data is usually attainable for B of the order of 100 attagauss, that is much lower value compared to 0.3 picogauss. Here, the total observable spectrum is shown as solid blue line. The intergalactic electromagnetic cascade component of the fit is dashed green line. Now we obtain the fits of the primary gamma ray spectrum, leaving the source and escaping into the intergalactic medium. The details of the fitting procedure are described in our paper, but to make the long story short, let us take a specific shape of the primary spectrum, shown as short dashed black line. Assuming the extragalactic background light model of Gilmore and collaborators, we account for the gamma-gamma absorption effect and adiabatic losses and obtain the solid black curve that fits the spectral energy distribution obtained with magic rather well. In this slide, we plot interaction rates for gamma rays and electrons for several values of the redshift. It is obvious that TeV gamma rays interact almost exclusively on extragalactic background light photons, while the electrons interact mainly on the cosmic microwave background photons. Similar spectral fits as described above were obtained for several other options of the extragalactic background light intensity with the same spectral shape but with 90, 80, and 70% of the nominal intensity. We note that the primary intensity at 1 TeV strongly depends on the extragalactic background light intensity normalization. The change of that normalization by only 30% corresponds to a significant change of the primary intensity by the factor of about 4. Secondary electrons and positrons get deflected in the extragalactic magnetic field and produce cascade gamma rays by means of the inverse Compton process. Stronger magnetic fields induce larger deflection angles and time delays. This time delay effect, in principle, could allow us to put some constraints on the AGMF parameters, namely its strength and coherence length. We note that for the range of parameters investigated in the present work, the time delay effect influences the observable intensity much stronger than the image broadening effects. Therefore, we neglect these latter effects. In fact, some of our predecessors listed here regarded the time delay approach to be rather promising. For instance, Plaga considered this method to be highly sensitive. Ichiki and collaborators believe it to be promising. We derive the 95% upper limits on the observable spectral energy distribution of our source using the publicly available Fermi-LAT gamma ray telescope data. Next, we make our model calculations using the publicly available LMAC code. Some details on the model setup are listed here. Finally, we obtain the model spectral energy distributions for various extragalactic magnetic field strength values, shown here as dashed black, solid black, green, and blue curves. All these curves are below the Fermi-LAT upper limits. Therefore, no limits on the extragalactic magnetic field strength could be set. The prospects of using this method in future are also rather dim. For instance, the effective energy threshold of Cherenkov telescope array appears to be far too high. It could not detect the cascade echo. Only new generation space gamma ray telescopes such as MAST could detect these cascade gamma rays, and only for the extragalactic magnetic field below about 10 attagauss. Please find more details about the MAST project in the cited paper and also on additional slides at the end of this presentation. The presentation is available via the conference site. Similar results for the extragalactic background model with somewhat reduced intensity, namely 70% of the original intensity, are still more discouraging. In this case, the intensity of the cascade component is still lower compared to the case of the original extragalactic background light model. We conclude that the uncertainty of the extragalactic background light intensity is a major source of systematics in this case. The Hess Imaging Atmospheric Cherenkov Telescope Array has detected a relatively nearby gamma ray burst. In this case, the gamma-gamma optical depth at about 1 TeV is modest, and the systematics are associated with the uncertainty of the extragalactic background light intensity is more moderate. Unfortunately, the primary intensity in this case is also rather modest, and estimates show that the prospects of constraining the extragalactic magnetic field parameters using these observations are not optimistic either. We conclude that the sensitivity of the Fermi-LAT space gamma ray telescope is not sufficient to detect the intergalactic electromagnetic cascade signal from GRB 190114C, even for the zero extragalactic magnetic field. It is unlikely that any strong constraints on the extragalactic magnetic field parameters will be set in the near future by this method. However, a precise measurement of the extragalactic background light intensity could significantly suppress one of the main sources of systematics. After that, it could become possible to exclude the option of a very weak, say 0.1 attagauss magnetic field in voids. Thank you very much for attention.